Jonathan Waite. I'm going to be a presentation on fields, fields of formal quotients, and Galois fields. And for a general overview of what we're going to be doing, we're going to be looking at our previous definitions and seeing how fields fit in with it, and using those previous definitions to have a better definition of a field to work with. Then we're going to look over a few different ways you can make fields, including fields of formal quotients, and finally Galois fields. So we'll start with definitions that we've had before. We have a group, which is has a set of elements, one operation, it's closed, associative, has an identity element, and inverses. Then we have an abelian group, which is a group where the operation is also commutative. Then we move to rings, which again have a set of elements, but this time have two operations. And it's an abelian group under the addition operation, and closed and associative under multiplication, and multiplication distributes over addition. We have the two lines there, which is the distributing over addition. And then one thing we have to make note of is we have addition and multiplication, but that's not necessarily the operations we're working with. It can be anything as long as that follows the properties, but for simplicity's sake, we'll just call it addition and multiplication. A commutative ring, it's a ring, and also the multiplication is commutative. That's what we would expect since it's called a commutative ring. And then there's integral domains, which are a commutative ring with no zero divisors. And a zero divisor is where you take two elements and multiply them together to get to the additive identity. So you take two elements that are not zero, and zero in this case being the additive identity. And then you multiply them together. Again, it doesn't have to be multiplication. And then you don't get zero to have no zero divisors. And then for our definition of field is an integral domain with multiplicative inverses. Now we're going to look at a more useful definition of field, because just having integral domain with multiplicative inverses doesn't give you really a full picture of what we're working with. So we go back through our definitions. Integral domain is a commutative ring is a ring. We take all the elements that we needed for all of that. We have a field is a set of elements with two operations, an abelian group under addition, closed, associative, commutative, and inverses under multiplication, no zero divisors, and multiplication distributes over addition. We can take those and we can have our field F, find the set F, two binary operations and elements. We can take set F under addition, the element 0, call that F plus, and take the set F not including 0 under multiplication with the element 1, call that F dot, are both abelian groups. And we take the 0 out of there, so we can have zero divisors. Because if we had zero divisors, that would give us two elements, multiply them together and get 0. And then we have 0, but set under multiplication doesn't have 0, so it wouldn't be closed, so it wouldn't be a group. So by defining it to be an abelian group, we disallow 0, disallowing 0 divisors. And we also have, again, multiplication distributing over addition. So some examples of fields. We have the rational numbers, the real numbers, the complex numbers, and the integers, mod p, where p is prime, and also Galois fields, which we're going to talk a little bit about later. And then some non-examples are the integers, because the integers do not have multiplicative inverses. And then also the integers mod p, where p is not prime. And in this case, it's because you can have zero divisors. So one thing you can do to make a field is start with a ring. We're going to work with the ring of integers. And you add elements that will behave in a way that will get you the properties of a field. So in this case, the integers under addition are an abelian group, but the integers under multiplication are not a group since they don't have inverses, but the integers under multiplication is commutative. So to form a field, we would need to add elements to act as the multiplicative inverses. Then we have our definition of the integers. We have like -3, -2, -1, 0, 1, 2, 3, out to infinity in both directions. So we'll need to add elements to work as the multiplicative inverses, and we have the fractions, 1 over 1/3, 1 over 1/2, 1 over -2, 1 over -3. But then if we just added that, we wouldn't have closure, because we could do something like adding 1/3 and 1/3, that would give us 2/3. So then we need to add all of the elements a over b, such that a and b are in the integers and b is not 0. And that leaves us with the rational numbers, which is why we know that rational numbers are a field. Then we'll move to fields of formal quotients. Our book defines fields of formal quotients as f of x, and we have p of x and q of x, where p of x and q of x are formal polynomials in the indeterminate x. Q of x cannot equal 0, and we use the normal rules of addition, multiplication, and cancellation. So in general, it's going to be of the form some polynomial over some other polynomial. And then one thing that will be useful when talking about Galois fields is characteristic. And this is the smallest number of sums of the multiplicative identity to get to the additive identity. And then again, sums, not necessarily sums, it's just the first operation. And then if this cannot be done, the characteristic is 0. So I have an example of this. In the rational numbers, we would have 1 plus 1 plus 1 and so on, and we would never get back to 0. So the rational numbers have characteristic 0. And then an example where we actually would have a characteristic is in the integers mod 3. We take 1 plus 1 plus 1, and that would get us back to 0. So the integers mod 3 have characteristic of 3. And then move on to Galois fields, which are also called finite fields. They are a field with a finite number of elements, and this number of elements is called the size. They only exist where the size is of the form p to the k, where p is a prime number and k is a positive integer. This p to the k is called a prime power. So for each prime power, there exists a finite field of that size, and all finite fields of the same size are isomorphic. For all finite fields, it's of the form p to the k, and they have characteristic p. Galois fields / finite fields are used in many areas of mathematics and computer science, including number theory, algebraic geometry, Galois theory, cryptography, and coding theory. Then I have examples of what a Galois field would be. In general, your Galois field, p to the n, is the field, the integers mod p adjoined with x over f to the x, where fx is any polynomial of degree n, which we get back from p to the n. And this polynomial of degree n has to be irreducible over the integers mod p. So an example of this is the Galois field 2 to the 2, which is the integers mod 2 adjoin x over x squared plus x plus 1. And in general, you need to make sure that your polynomial there is irreducible over the integers mod that you're using. Because if it's not, then it's not actually a Galois field. So in conclusion, we talked about fields, how they work off of our previous definitions. Talked a little bit about different types of fields, how to make them. Went over fields of formal quotients, and then finally Galois fields. Thank you.